So this was a weekly homework, and you can ask your doubts related to this weekly homework. The homework was related to the chemical bonding and the structure from page 1 to page 12. I'm talking about the last week. As this week is from 13 to 24, so last week is from 1 to 12. Any doubt on page 3? Page number 3, any question or a part? If you have a doubt, you can ask. No doubt? Okay. Any doubt on page number 4? The third part, describe and explain the relative thermal stability of hydrogen halides. The thermal stabilities means, as you can see, you have the boiling points are given and the bond strength are also given. Page number 3, part 3, okay. So you want to compare the thermal stability means the strength of the bond you want to compare. So we have 526 kilojoule per mole, the energy needed to break the hydrogen fluorine bond. 431 kilojoule per mole, it's the energy which we need to break hydrogen chlorine bond. And hydrogen bromide bond, we need 366. And hydrogen iodide bond, we need 229. So what is happening to the energy needed to break the bond? So that is decreasing. So what happened to the thermal stabilities? Because we have hydrogen fluoride is there, then hydrogen chloride, then hydrogen bromide, and hydrogen iodide. So we'll mention the thermal stability. As we are going down the group, it is decreasing. And why the thermal stability is decreasing? As the strength of the bond, hydrogen halide bond is there, that strength of the bond is decreasing. And why there's a strength is decreasing? Because these are the non-metals, they will have a covalent bonding. So fluorine is smaller in size as compared to that of chlorine. Chlorine will be larger in size as compared to fluorine, and then we compare bromine, it will be much larger as compared to that of chlorine. So the covalent bond, the strength of the covalent bond depends on the attraction between the lone pair, between the shared pair and the nucleus. So as the distance from the nucleus, as we go down the group, the size of an atom increases. So the distance from the shared pair and the nucleus will also decrease, also increase, sorry, I mean. So as the distance is increasing, so what will happen? The strength of the bond will decrease. And another factor, that is the shielding effect. Like fluorine is having 2 shells, chlorine will have 3 shells, bromine will have 4 shells. So as the number of the shells increase, there will be a greater shielding effect. So the points which will score the marks here, one thing you will mention, as we go down the group, we observe that the bond strength is decreasing, so the thermal stability is decreasing. Why the thermal stability is decreasing? Because the size of an atom increase. So if the size of an atom increase, the distance, the attraction between the shared pair and the nucleus is decreasing. And the second thing, that there are more electron shells, as greater number of electron shells, so greater shielding effect. So this shared pair will not experience the same force when it will be with chlorine or with fluorine. Is it clear, this one? The reason? So these are the points you should refer the 3 points. Page number 4, any doubt? Page 4. Page 5, any doubt? The structural isomer, this is when they have the same molecular formula and different structure, we call structural isomers. Then explain sp2 and sp3 hybridization. Explain how sp2 and sp3 hybridization can happen or occur in carbon. So what is the meaning of the term sp2 hybridization? The term sp2 hybridization means like when it's actually an overlapping of the 2s, like when 1s and 2p orbitals overlap with each other or they have the same energy. So sp2 hybridization means, and specifically they mention in the carbon, when we write the configuration of the carbon, carbon is 6 and 12. So the configuration will be 1s2, 2s2, 2p2. But what happened in excited state, that one of the electron from the s orbital jumps to the p. So this will become 2s1 and 2p3. So we have 1s, we have 2s, and in terms of energy, when we draw them, this is normally what happened, like 1s is having a lower energy, then 2s is having a relatively higher energy, then we will have 2p, x, y, and z. So this one is 1s, this one is 2s, this is 2px, 2py, and 2pz. This is normally. Now, what happened in hybridization? So this is one electron here, and single electrons in the p orbitals. Now, in the hybridization, what happened is that the overlapping of the orbital happen or the energy becomes same. Means 1s energy does not change. One of the 2s in sp3 hybridization, what actually happened? They all have the same energies. This is what happened in sp3 hybridization. This is 1s, this one is 2s, this is 2px, 2py, 2pz. So they all have the same energies. What we call this hybridization, we call sp3 hybridization. But in sp2 hybridization, so 2s and two of the p orbitals, 2px and 2py energy is same, and 2pz energy is different. So this is 1s, this one is 2s, 2px, 2py, and then 2pz. This is called sp2 hybridization. Because 2s and two of the p orbitals, they have the same energy. So how we write like sp2 or sp3 hybridization? If you want to define sp2 hybridization, so we'll say the energy of the 2s and the two of the 2p orbitals, it will become same, or we can also use the term overlapping of the orbitals. So we can also say overlapping of the 2s orbital with 2p orbitals result in hybridization. So in sp2 hybridization, one of the s and two of the p's have the same energy, another p is having a higher energy. So because their energy becomes same, so we call sp2. But in sp3 hybridization, what happened? One of the s and the three of the p's, they all have the same energy. So that we call sp3 hybridization. Is it clear? The concept of hybridization? Then state the bond angle. Yes, sure, I will repeat. The term hybridization refers to when the energy of different orbitals becomes same, we call hybridization. We can have sp3 hybridization, we can have sp2 hybridization, or we may have sp hybridization. What is a normal energy? Like we have 1s, then we have 2s, and then we have 2px, 2py, and 2pz. This is normally. But if there is an sp3 hybridization, so what happened? That one of the s orbital and three of the p orbitals, they all get the same energy. So if one of the s and three of the p, they all get the same energy, what we call this hybridization? We call sp3 hybridization. And we can also say the orbital will overlap as they have the same energy. You can also use the term overlapping of the orbital. What happened in sp2 hybridization? That 2s, 2px, 2py will have the same energy and 2pz will have a higher energy. So when two of the p orbitals and one of the s orbital have the same energy, we call that as sp2 hybridization. And what happened in sp hybridization? Then 2s and 2px have the same energy, 2py and 2pz have a different energy. So as a result, what will happen? One of the s and one p have the same energy. We call that as sp hybridization. So three types of hybridizations are possible: sp3, sp2, sp hybridization. When a carbon is forming a single bond, it will have sp3 hybridization. When carbon is having a double bond, it will have sp2 hybridization. When carbon form a triple bond, it will have sp hybridization. So next question is actually related to state the bond angles. The next is state the bond angles normally associated with each type of hybridization of a carbon. What happened in sp2 hybridization? In sp2 hybridization, what will happen? The carbon, because will form a double bond. If carbon form a double bond, like one carbon will have a double bond, so remaining two bonds are available. When I predict the geometry of this type of a structure, this I'll consider as one bond pair when I predict the geometry. So three bond pairs are there. Whenever three bond pairs are there, it will be a trigonal planar structure with a bond angle of 120 degrees. But when we say sp3 hybridization, in sp3 hybridization, carbon always form four bonds, like always form a single bond with another atom. So as a result, what will happen? When four bond pairs are there, because when we consider the bond pair, 1, 2, 3, and 4. So when four bond pairs are there and there is no lone pair, the bond angle will be 109.5 and it will have a tetrahedral structure. So the bond angle will be 109.5 degrees. So whenever, if it is sp3 hybridization, it means carbon will form a triple bond with another atom. So one side always is a triple bond and then a single bond. What will be the geometry of this? So this will count as one, this we count as another. So the bond, it means it has a two bond pairs. So we'll say it will have a bond angle of 180. But when it is sp2 hybridization, it means with one atom, carbon definitely form a double bond. So the remaining are two single bonds. When we predict the geometry, one side double bond and then we have a single bond. But when double bond or triple bond, when we predict the geometry, we consider them as a single bond. So it means it will be three bond pair. So the bond angle of the three bond pairs is always 120. sp3 means the carbon maximum can form a single bond with another atom. So if it is forming a single bond, so four different orientations, it will form a bond. And when four bond pairs are there and there is no lone pair, it means it will have a bond angle of 109.5 degrees because it should be a tetrahedral structure. Is it clear? This concept about the structure and the orbital overlapping? Any doubt? So if they ask for sp angle, you can also predict that it will be 180 because carbon will form a triple bond with another atom and it will form a single bond with one. So definitely it will be a 180 degrees the bond angle. Page number 6, any doubt on page 6? Page 6, any question or a doubt? Page 6, page 7, diagram part, part 2. Okay. The bonding between the carbon and the nitrogen before pi and sigma. Draw a dot and cross diagram to represent the molecule, represent the bonding in a molecule of ammonia and state the shape of this molecule. So nitrogen belongs to group 5, so it will share 3 electrons. And 2 unshared electrons, the lone pair. So if you want to predict the geometry, there are 3 bond pairs. And there is 1 lone pair. When we have 3 bond pair and there is 1 lone pair, what we say? The structure of this, it will be according to like trigonal pyramidal. Yeah, that's right. Trigonal pyramidal it will be. Or you can also say pyramidal with a bond angle of 107. Do we always draw charge cloud or can I draw orbitals? When they ask for this question, as you have to draw, like you have to show a sigma in the pi bond. So sigma bond is by overlapping of the orbital. So how the overlapping of the orbital happen or occur? Like as you can see, between a carbon and the hydrogen, we have to, as the bonding between the carbon and nitrogen consists of 1 sigma and 2 pi bonds. Sketch the shape of a sigma bond and 1 sigma bond and 1 pi bond in the space below. First, you can draw the orbitals. Like the best way to draw the overlapping is share the electron density map in overlapping of the orbital. So when I write the configuration of a carbon, it is 1s2, 2s2, 2p, 2p2 is there, but in excited state it will be 1s2, 2s2, 1s2, 2s1 and 2p3. So means what is available for a bonding? That 2s is available. Like the available for bonding, we have 2s available, 2px is available, 2py is also available, and 2pz is also available. These are the orbital available from the side of the carbon. So carbon is forming, like here's a sigma bond. This one of them is a sigma and 2 of them will be a pi bond. What about the nitrogen? When we write the configuration, it is 1s2, 2s2, 2p3. So in case of a nitrogen, the only orbitals which are available is the 2px, 2py and 2pz, and there's a single. So means either if I want to show the orbital overlapping, so either I can show an overlapping between the 2s and 2p, like I can show an overlapping between the 2s of the carbon with 2px with the nitrogen and show complete overlapping, so it will be a sigma bond. That is one way. Or I can also show that 2px of the carbon and 2px of the nitrogen that can also overlap, and that will also result in a formation of a sigma bond. So how we represent that, because it's a complete overlapping. So example, I'm representing the 2px of the carbon with 2px of the nitrogen. So this is say 2px of carbon and this is 2px of the nitrogen. So as a result, they will overlap with here. So it will be a complete overlapping. So what is the probability of finding electron? If you want to find the electron, the maximum possibility or maximum probability in this region, we can find the electron. So when I show this representation, like this is fine, overlapping of the orbital, or the best way to show the electron density cloud. Electron density cloud means like here is say carbon, here this is carbon nucleus, and here is a nitrogen nucleus. In between, as you can see, the width of the electron density cloud is greater. So what it shows the possibility of finding electron is maximum in this region. Is it clear? And how to show the pi? So which one you have to draw? Like you can draw, as I mentioned, you can draw the 2s with 2px. That's also fine. Or you can also draw 2px with 2px. So even you can draw this one, it's acceptable. You can draw the second one, that's also acceptable. But students doing EdExcel, usually they prefer this diagram. And for Cambridge student, they prefer that electron density cloud. Like you show the electron density cloud. But those who are taking EdExcel, usually they accept, like most common in the marking scheme, you will find that if they ask to draw sigma bonds, you have to show the overlapping of the orbital directly. But for students taking Cambridge, they prefer that you show the electron density cloud between the two nucleus. Then how to represent the pi? So 2px is overlapping. So this carbon example, this is 2py of the carbon because x is overlapping, and this is 2py of the nitrogen. So there will be attraction. There will be attraction between them, like there will be attraction from the top or the bottom. So how we represent that, as there is attraction from the top or the bottom. So I can draw like this is a carbon, this is a nitrogen. So I can have electron density at the top or I can have electron density at the bottom. So you can represent the electron density, the pi bond in this manner. This is how we represent a pi bond. It's not an overlapping, like this is a possibility or probability of finding electron is maximum. We can either find them at the bottom or we can find at the top. The overlapping orbital can only happen because for a bonding, what is available orbital for the carbon? For a carbon, only available is 2s, 2px, 2py, and 2pz. These are the available orbitals. But in case of a nitrogen, because 2s is already complete, so it will not overlap. So available is 2px, 2py, and 2pz. These are the available orbitals for overlapping. For a pi bond, you will draw in the same manner for both student taking Edexcel or a Cambridge. You will draw in the same manner. But for a sigma bond representation, you can represent in this manner, or yeah, you can shade for the pi, like shade any one part. Shade one part and leave the other part unshaded. Because this is a possibility that electrons might be here or electron might be on the top. So we shade the region. Like it can be at the top or it can be. So we shade one of the region. And how we represent the sigma bonds? In this manner. Or if you want to show the overlapping of the orbital, you can represent in this manner. It's the same thing, no difference between the two diagrams. Is it clear? So how you draw a sigma is by overlapping of the orbitals. You can draw in this way, the overlapping of the orbital, or you can show the electron density cloud that the two nucleus, the dots are representing the nucleus and probability of finding electron is maximum in this region. For a pi bond, there will be attraction from the top and the bottom. So these dots are representing the nucleus. So you can find electron within this region. That is the pi bond. So pi bond is by when axis is parallel and partial overlapping, and sigma bond when there is a complete overlapping of the orbitals. If you want to show the carbon, like the overlapping of the carbon 2s with nitrogen 2px, so how it can be done? Because s orbital is spherical, so this will be carbon, and the nitrogen 2px, so this will be the nitrogen 2px. So what shape it will be? If I'm showing the if I'm representing the orbital overlapping, so maximum probability is there near the nitrogen because the nitrogen 2s is there, and this is representing, say, the carbon. So both ways are acceptable here. Either overlapping of the orbital or the electron density cloud.
Wait one
Yes,
second.
sorry.
Okay, so could you draw the charge cloud again? Just I wanted to ask something on the diagram. Just the charge cloud with the two nuclei. Yes. Okay, wait, I'll annotate on the screen. One second.
Yes, yes.
Okay, so I saw diagrams which had this as well. What does this signify?
What it
The
shows,
fins?
yeah. What it shows, like example, you have a carbon and nitrogen. Say this is a p orbit px, and this is also a px. So because of the overlapping, what happened? The probability of finding electron is maximum between the two atoms. So, and the probability of the electrons to be on the other side is minimum, but there is a chance. So as a result, what will happen? How we draw this? We draw in this manner. It shows that because this electron belongs to carbon, it can be here or it can be here. But the chance of finding this electron is maximum between the carbon and the nitrogen. Same way, the electron of a nitrogen can be on the right or the left, but the probability or the chance to have this electron between the carbon and nitrogen is maximum. But still, there is a chance that this electron might be on the other side. That's why we draw these fins.
Okay, so both ways work.
Yeah, it will work both ways. Like when I drew, look, when I drew this electron density cloud, when I drew the electron density cloud, I did not draw the nucleus here at the edge. Where I drew the nucleus, I drew a nucleus this point. So what it shows that the chance of finding electron, I can find electron anywhere in this region, maximum. But still there is a chance that I may have electron on the other side as well.
But even with the fins, they have the nuclei in the same position that you have in the oval, not at the edge.
Yeah, the same, because with the fins also, the nucleus is here. This is representing the position of the nucleus. This is the position of the nucleus. This is the, oh, look, one is, this diagram is the diagram which shows the orbital overlapping. Like I drew the orbital overlapping. And this diagram is actually showing the electron density cloud, orbital overlapping with the electron density cloud as well. So this is acceptable. This is also acceptable. Both of them.
Okay, and if it was s orbital with a p orbital, only one side will have a fin, right?
Yes, one side.
Okay.
Page 7, any doubt? Page number 7. Page 8. Page 9, any doubt? Page 8, part 2. Okay. Two molecules have the same shape, suggests why the boiling points are significantly different. So they have the same shape, but why the boiling points are different? Remember one thing, that the intermolecular force, the London dispersion force, increases as the number of electron increase. So you can see the bromine is having more electron. The bromine is having more electrons as compared to that of chlorine. So as there are more or greater number of electrons, greater the number of electrons, greater the dipole-induced dipole forces. So two molecules have the same shape. Why the boiling points are significantly different? First thing, we will mention the type of the intermolecular force. Like example, chlorine is there bonded with 3-fluorine, and bromine is there. It is also bonded with 3 of the fluorine. So they will have, because bonds are polar, and as a result, if it is having a net dipole moment, so between the molecule, like if there is another molecule of a chlorine trifluoride, they will have dipole-induced dipole force. And the dipole-induced dipole force increases as the number of electron increase. So the boiling point of ClF3 and BF3, why there is a difference? So the main reason is because of the dipole-induced dipole forces. And they will have the permanent dipoles as well. Why permanent dipole? Because when the bonds are formed between the two atoms which are having a difference in electronegativity, so the bond will be a polar. Because of the existence of the polar bond, they will have dipole forces as well, or permanent dipole force. But the dipole-induced dipole force increases as the number of electron increase. Is it clear? No, the both forces does not increases with the number of electron. The dipole-induced dipole forces increases as the number of electron increase. The dipole force or the permanent dipole depends on the difference in the electronegativity. So if there is a greater difference in electron, like example, we have fluorine, chlorine, bromine, and iodine. as we go down the group, the electronegativity decreases. So if I have fluorine bonded with chlorine, they will have a smaller difference in electronegativity as compared to fluorine bonded with bromine. They will have a greater difference in electronegativity. So as a result, there will be large permanent dipoles will be there when there's a bond between bromine and fluorine as compared to fluorine and chlorine. So they will have a strong permanent dipole force. Another reason that because bromine is having more electrons, so the London dispersion force or van der Waals forces will also increases. So 2 mark for mentioning the difference in electronegativity increase. So there will be a stronger permanent dipole in between boron and fluorine as compared to fluorine and chlorine. And the other 2 marks are they have a dipole induced dipole forces which increases as a number of electron increase. So bromine is having more electron than chlorine. So as a result, it will have a stronger dipole induced dipole force as well. So as a result, both forces are stronger in fluorine bromine as compared to fluorine and chlorine. That's why it will have a high boiling point. Next, we have page 9, any doubt? Part 2 and 3. Suggest why the melting point of a chlorine, melting point increases from Cl2 to ICl. It's the same reason. When Cl2 is there, what kind of force it will have? It will have only dipole induced dipole force. London this. When BrCl is there, they will have the permanent dipole, like dipole and dipole induced dipole. When ICl is there, it will have dipole induced dipole force is also there, and dipole induced dipole force is also there. And the same reason, because as we go down the group, the electronegativity decreases. So when I compare a bond between carbon and chlorine and bromine, that will have a smaller difference in the electronegativity as compared to chlorine and iodine. So they will have a large difference in the electronegativity. So large difference in electronegativity means there will have a stronger dipole force, because the dipole force depends on the difference in the electronegativity. And the second reason, the dipole induced dipole force depends on the number of electrons. So when you count the number of electrons, like chlorine is 35 and chlorine is 17 and 17, so total 34 electrons. But bromine and chlorine will have more electrons, and iodine and chlorine will have the most electrons. So as a result, what will happen? That's why the ICl. So suggest why the melting point increases. I'm explaining the both questions together, 2 and 3. So suggest why the melting point increases as we move from ICl, like Cl2 to ICl. Because the main reason is that the intermolecular forces increases. The intermolecular force gets stronger, and both the dipole induced dipole force or the London dispersion forces, both forces increases. And the second one is the reason for that, like suggest which of these molecules have the largest permanent dipole. So which will have a largest permanent dipole? ICl will have a largest permanent dipole because it is having a greater difference in the electronegativity. So this was page 9. Page 10.